There's a chapter in Earth's story that feels straight out of a science fiction blockbuster, but it wasn't imagination. It truly unfolded, reshaping our world into something alien and almost unrecognizable. Picture stepping outside into air, so saturated with oxygen it would make you feel lightheaded in minutes. A world where a single lightning strike could ignite even rain-soaked forests, turning them into raging infernos. A time when insects ballooned into giants, with dragonflies as wide as your arm span and millipedes stretching longer than your living room sofa. This was life during the Carboniferous period, when oxygen levels in the atmosphere soared to around 35%, nearly double the concentration we breathe today. For an astonishing 60 million years, this oxygen-heavy environment supercharged evolution in ways that seem impossible by modern standards. And hey, if you enjoy these deep dives into Earth's strangest eras, give this a like or subscribe. I'd also love to know where you're watching from. Last time I spotted comments from Miami, Manchester and Melbourne all in the same thread. The internet really is its own bizarre ecosystem, isn't it? But let's stay focused. This isn't only a tale about oversized bugs. It's about a rare moment in our planet's history when the very chemistry of the air rewrote the rules for life itself. A set of conditions that existed once and can never repeat again. And it all started with what scientists often call an evolutionary accident. To journey back to the late Carboniferous roughly 300 million years ago is to step into a world mid-transformation. The continents weren't scattered as they are now. Instead, they were slowly converging into a supercontinent known as Pangaea, a colossal landmass stretching nearly from pole to pole and bordered by one vast global ocean. The land surface was still relatively new territory for life, raw and humid, but the real revolution of this time wasn't in the shifting continents, it was in the forests. The Carboniferous gave rise to Earth's first expansive rainforests, and they were nothing like the ecosystems we recognize today. Towering over the swamps were lycopsids, club moss relatives that grew up to 100 feet tall, the height of a 10-story building. Despite their size, these giants weren't true trees. They had hollow, water-filled stems and reproduced with spores rather than seed. Alongside them thrived seed ferns, massive horsetails and fungi that reached 20 to 25 feet into the air like strange alien towers. This was so early in plant evolution that flowers, fruits and grasses hadn't yet appeared. The buzz of bees, the shade of oaks, those were still hundreds of millions of years away. These Carboniferous forests were dense, damp and dim, ferns tangled with vines in endless mats, and the floor was a patchwork of decay. As vegetation died, it piled up in waterlogged soils, forming vast peat bogs over immense stretches of time. This carbon-rich material compressed into the coal seams that humans would later mine and burn. But this lush new world also pumped enormous amounts of oxygen into the atmosphere. Photosynthesis outpaced decomposition, releasing more oxygen than ever before in Earth's history. Some estimates put the concentration as high as 35%. At those levels, humans today would feel dizzy after only a few breaths, and even a candle flame would burn with almost frightening intensity. And for one particular group, these conditions were paradise. Arthropods, insects, spiders, scorpions, and millipedes didn't just thrive, they exploded in size. Meanwhile, vertebrates were still at the beginning of their story. Amphibians had made their first moves onto land and some grew large, reaching 6 feet or more, but they remained tied to moist skin and aquatic eggs. Early reptiles had only just emerged, developing protective scales and shelled eggs that would one day allow dinosaurs to rise. But for now, they were secondary players. This was an age ruled by creatures in exoskeletons. So why exactly did insects become so enormous? The answer lies in the way they breathe. Unlike mammals or reptiles, insects don't have lungs or diaphragms. Their respiratory system is an intricate network of tiny tubes called tracheae, which deliver oxygen directly to their cells by diffusion. Think of it like a body laced with thousands of microscopic snorkels. Oxygen seeps in through openings called spirochetes and drifts passively into tissues. It's simple and elegant, but not efficient for large body. The bigger the insect, the harder it is for oxygen to reach its inner tissues without some form of active pumping. In today's atmosphere, this limits how large insects can grow. Take, for example, the giant weta of New Zealand, among the largest insects alive today. It can grow up to 7 centimeters long and weigh around 70 grams. Impressive, but still something you could easily hold in your hand. But in the Carboniferous, oxygen was so abundant that even large insects could meet their metabolic needs through diffusion alone. This allowed them to grow to spectacular proportions. In a sense, oxygen functioned like an evolutionary steroid, and this isn't just a theory. In 2007, scientists at Arizona State University raised modern insects in controlled environments with different oxygen level. The results were striking. Species raised in oxygen-rich chambers grew noticeably larger than their counterparts in normal air. The same genetic potential for gigantism still exists within insects today. It's just capped by our thinner atmosphere. Now picture yourself standing in a Carboniferous swamp forest. The ground beneath your boots is spongy peat, built up from countless generations of decayed plants. The air is not only humid, but thick with oxygen, far more than your lungs are used to. You'd feel almost intoxicated, your breathing quickening without panic, simply because of the chemistry. At these concentrations, the world was also highly flammable. A single spark or lightning strike could ignite even soaked wood into raging fire. What we think of as spontaneous combustion could have been an everyday reality here. Around your feet, roots twist across the muck like living veins, while tiny arthropods scuttle everywhere. Early amphibians lurk in the shadows, creatures with too many legs and features that don't quite match anything familiar. But it's when you raise your eyes that the true alienness hits. Above the swamp canopy, the filtered light reveals flying creatures that seem impossible by modern rules. One flutters past. It looks vaguely like a bird, if birds had never evolved and evolution had chosen a different experiment. It's not a bird at all, but a Paleodictyoptera, among the earliest winged insects ever to take to the sky. With wingspans ranging from 15 to 22 inches, they were giants by insect standards. Despite their size, they weren't hunters. They glided gently through the forest, sipping plant sap with long needle-like mouthparts. Their wings, 4 main ones, plus 2 smaller lobes near the thorax, were patterned with intricate veins, resembling stained glass windows suspended in the air. These prothoracic winglets may have been evolutionary leftovers from gill structures, a hint at how insect wings first arose. Though fossils can't tell us their colors, it's possible their wings shimmered with patterns or iridescence, like massive living kites drifting through the Carboniferous sunlight. Their very existence marked a turning point. For the first time in history, animals had conquered the sky. Flight was no longer impossible. Evolution had unlocked an entirely new frontier, but not every aerial giant was gentle. Some turned the Carboniferous skies into hunting grounds. Imagine a predator with 4 independently moving wings, each beating like a size as wide as marbles, able to see nearly everything around it at once. Legs barbed like grappling hooks, forming a deadly net to snatch prey mid-flight. This was Meganeura, the dragonfly-like titan with wingspans up to for millions of years. It was the top predator of the skies, striking with lethal accuracy. Fossil evidence suggests Meganeura hunted not just insects but also small amphibians and perhaps early vertebrates. Its juveniles likely lived in water as nymphs, just as modern dragonflies do, predators even then, feeding on tadpoles and aquatic creatures before emerging as flying killers. Its wing structure was so strong and complex that it could maneuver with surgical precision, hovering, diving, and striking with devastating speed. With an estimated success rate over 90%, few creatures escaped once Meganeura locked. And while the skies swarmed with these flying monsters, The ground was home to equally nightmarish creatures. Something moves in the undergrowth, armored, many-legged, its silhouette more log than animal, until it bent. This was Pulmonoscorpius kirktonensis, the largest scorpion to ever stalk the land. At 28 inches long, roughly the length of a house cat, it was a formidable predator. Its massive pincers crushed prey, while its venomous stinger arched over its back, capable of dispatching amphibians and early reptiles alike. Its body was plated in thick armor, its eyes adapted to low light, and it likely detected vibrations in the ground to pinpoint prey long before it arrived. Pulmonoscorpius didn't chase, it waited, perfectly still in the shadows, then struck with terrifying precision. Fossil finds in Scotland place it in dense swampy forests, ideal for ambush hunting. Yet even this monstrous scorpion was not the ultimate giant. That title belonged to Arthropleura, the largest land-dwelling invertebrate to ever live. At over 8 feet long, it resembled an enormous millipede armored in overlapping plates, crawling slowly through the Carboniferous swamp. Fossil trackways show its size with eerie clarity, some impressions so large you could lie down inside them. Despite its fearsome appearance, Arthropleura appears to have been an herbivore, munching on decaying plants and forest debris. It was a lumbering giant, harmless to animals but a living nightmare in appearance. The Carboniferous was Earth at its strangest, a time when oxygen tipped the scales of life, and the result was a planet of giants, both terrifying and wonderful. Instead of ripping apart prey with fangs, it probably spent its time grinding down soft vegetation, turning the damp forest floor into mulch one bite at a time. But in this ancient world, raw size alone was a weapon. Being enormous meant fewer threats. Even formidable hunters like Pulmonoscorpius would have thought twice before taking on a creature armored like a tank and weighing more than anything else in its environment. No vertebrate of the Carboniferous age could have stood against it in a head-to-head encounter. Fossils of this behemoth have been uncovered across Scotland, Germany and North America, showing it was a common resident of swampy wetlands. These were places where fallen trees and plants decayed rapidly, piling into thick layers of organic matter that fueled entire ecosystems. Yet, for all the remains we've found, one crucial piece is missing: its complete head. We still don't know exactly what its mouth looked like or how it reproduced. Did it stay to protect its eggs? Did it dig burrows in the damp soil? Those questions remain unanswered. This is what makes so many of the Carboniferous giants fascinating. The mysteries are just as captivating as the facts. That period in Earth's history was a massive experiment in evolution, testing the boundaries of what life could achieve in a world saturated with oxygen. One striking example is Megarachne cervinae. For decades, scientists, the media, and even textbooks called it the largest spider that ever lived. With its massive body and sprawling legs, it was imagined as a nightmare predator lurking in the swamps. But in 2005, paleontologist Paul Selden and his team revisited the fossil and flipped the story upside down. Megarachne wasn't a spider at all, not even an arachnid. It was a eurypterid, a long-extinct group often nicknamed sea scorpion. Instead of weaving webs or stalking the undergrowth, this creature crawled along river bottoms, pushing through sediment with paddle-like limbs in search of prey. Eurypterids were distant relatives of scorpions, horseshoe crabs and trilobites, predators and scavengers that thrived in aquatic ecosystems long before fish and amphibians ruled the shallows. Even if it wasn't a spider, Megarachne was still massive for its kind. Fossil evidence suggests its body measured nearly 2 feet across, making it one of the largest freshwater eurypterids known. Its sturdy limbs were shaped for digging into soft mud, raking detritus, and trapping small organisms such as worms, insect larvae or tiny crustaceans. The preserved fossil shows a broad armored carapace with segmented sections that resembled a spider's body, which is what misled researchers for so long. The crucial details were missing: No spinnerets, no fangs, no signs of adaptations for breathing air. Clearly this was a water dweller, living in shallow, oxygen-rich swamps where rotting vegetation fueled entire food webs of scavengers and filter feeders. Within that ecosystem, the Megarachne sat high on the chain. Its evolutionary cousins included giants like Eucalyptus and Tetragotus, some of which grew over 8 feet long. Compared to them, Megarachne was modest in size, but it represented a unique step. The rare Eurypterid adapted to freshwater instead of the sea. That transition marked an important moment as marine life began inching toward terrestrial dominance. Its wide, flattened limbs and heavy armor gave it a terrifying appearance, something alien to our art. That strangeness alone taps into a primal fear, creatures that don't fit the familiar rules of animal form. But not every threat of the Carboniferous relied on bulk or strength. Some gained an edge simply by arriving first. Trigonotarbids, for instance, were among the earliest land-based predators. These arachnids breathed air, walked confidently across the undergrowth, and had abandoned water long before many other groups. Their lineage stretches back at least 419 million years, well before the Carboniferous boom. They looked like spiders, and for decades were lumped together with them, but they weren't true spiders. They had no silk glands and couldn't spin webs. Instead, their bodies were short and armed. A hard carapace shielded their head and thorax, while their segmented abdomen was plated for extra protection. Their 8 legs, lined with spines, were perfect for maneuvering through cluttered leaf litter. Their hunting style was brutal. They targeted small, soft-bodied invertebrates, grabbing them with sharp jaws and holding them fast with their legs before consuming them alive. Some species were barely a few millimeters long, while the largest reached about 2 inches. Their advantage was stealth and size, small enough to hide from the giant predators of their world. They breathed using book lungs just like scorpions and spiders today, and their internal anatomy shows astonishing evolutionary sophistication. Fossils from the Rhynie Chart in Scotland preserve them in incredible detail, down to tiny hairs on their legs, and the delicate structures of their breathing organs. These early pioneers thrived for millions of years, but in time they faded. No great extinction wiped them out. No predator ended their reign. They were simply overtaken by newer arachnids, true spiders and scorpions that brought something Trigonotarbids never had: silk. That innovation changed everything. Yet while some creatures faded, others evolved armor as their weapon of choice. One such animal was Lepidoculeus, nicknamed the Excalibur worm. Despite measuring only a few millimeters long, it may have been the most heavily armored creature of its size in Earth's history. Living more than 400 million years ago in the Devonian, long before Carboniferous rainforests existed, this worm carried a fortress on its back. Its body was encased in overlapping calcite plates that worked like medieval chainmail, forming a flexible but nearly impenetrable shell. Fossils discovered in Western Australia reveal how these plates interlocked like tiny shields. When threatened, the worm could curl into a ball, showing only the armored exterior. For predators of its size, it was untouchable. This remarkable design earned it the Excalibur nickname, like a blade seemingly too perfect for its age. But armor came with trade-offs. Heavily protected, it was slower and less mobile. Its ability to spread to new environments was likely limited. We don't know exactly what it ate. Possibly organic debris, microbial mats or detritus on the seafloor. It left no bite marks behind, only an evolutionary marvel preserved in stone. For a while, sheer defense was enough, but as new predators arose and vertebrates gained dominance, the Excalibur worm vanished quietly into history. To truly understand these strange animals, we have to look at their breathing system. Arthropods had a respiratory setup that worked brilliantly in the oxygen-heavy atmosphere of the Carboniferous, but that same design carried hard limits when oxygen levels fell. Modern insects breathe through spiracles along their body, which connect to branching tubes called trachea. These deliver oxygen directly to tissues through simple diffusion. It's an efficient method for small bodies, giving insects extremely high metabolic rates that allow rapid flight and fast movements. But diffusion only works over short distance. The bigger the insect, the harder it is for oxygen to reach the center of its body. In today's 21% oxygen atmosphere, that sets a size ceiling, but in the Carboniferous, oxygen levels soared to around 30. With that much oxygen, diffusion could cover far greater distances, lifting the size limit. Suddenly, massive dragonflies and colossal millipedes weren't just possible, they were inevitable. These giants also had astonishing strength. Insects relative to body size are stronger than any mammal or reptile. A dung beetle can haul more than 1,100 times its body weight, the human equivalent of dragging half a dozen buses. Rhinoceros beetles, leafcutter ants and trapjaw ants all showcase incredible ratios, easily surpassing tigers, bears and even gorillas. Now imagine those same mechanical advantages at the size of a dog or larger. That was the Carboniferous reality. But this golden age couldn't last forever. The end came not with catastrophe but with gradual change. Around 305 million years ago, Earth's equatorial swamplands began to shrink. As the continents drifted together into Pangaea, rising mountains altered rainfall, and lush rainforests fragmented into peat bogs dried, fire spread more easily, and fungi evolved to decompose wood more efficiently. Oxygen levels declined from their peak, and the giants could no longer breathe enough to sustain their massive body. Reptiles, with their watertight skin and amniotic eggs, thrived where amphibians and giant insects faltered. By the dawn of the Permian, the age of invertebrate giants was over. Smaller, more efficient species survived, but the era of titans had passed. It's tempting to imagine a different world, one where insects stayed huge and ruled alongside vertebrates. But lungs, circulatory systems, and vertebrate adaptability gave our ancestors the ultimate edge. Scale mattered, and arthropods could no longer compete. Even so, echoes of that world survive today. Dragonflies fly with the same mechanics perfected 300 million years ago. Millipedes still carry their segmented armor. Mantises hunt with dinosaur-like patience. They may be smaller now, but the legacy of their giant forebears lives on. And the reason such a world will never return lies in one word: lignin. This plant polymer gave trees their woody strength, letting them tower skyward. But for millions of years, nothing could break lignin down. Dead plants piled up, trapping carbon underground and leaving free oxygen in the atmosphere. That one-way flow drove oxygen to its Carboniferous peak, until white rot fungi evolved the ability to decompose lignin. With that breakthrough, Earth's carbon cycle balanced again. Dead wood could rot fully, releasing carbon dioxide back into the air. From then on, oxygen levels never again reached Carboniferous heights. The world of giant insects was gone, and it will never return. The earliest versions of these fungi are preserved in amber dating back to the late Carboniferous, right at the moment when atmospheric oxygen began its long decline. In today's forests, fungi that can break down lignin are everywhere. Every decaying branch or fallen trunk quickly becomes home to communities of decomposers that can strip it apart entirely. Modern trees still rely on lignin to give them structure, but instead of being locked away forever, it now cycles back into the environment in balance with carbon processes. The rise of lignin-digesting fungi ensured that the planet would never again reach oxygen levels of 35%. This is a textbook example of how life reshapes the chemistry of the planet itself, setting up feedback loops that persist for hundreds of millions of years. Fungi, however, were not the only organisms to tip the balance. Roughly 50 million years ago, termites evolved. bringing with them an incredibly efficient system for recycling wood. Their specialized gut microbes allow them to break down cellulose and complex plant material far more thoroughly than most creatures could. Even today, termites consume and process about 1/3 of all dead wood across tropical regions. Between fungi, bacteria, termites and other decomposers, Earth gained a non-stop recycling crew that prevented the massive long-term carbon burial which once pushed oxygen into extreme highs. It wasn't simply the disappearance of swampy forests that brought the Carboniferous oxygen era to an end. It was also the rise of organisms that only existed because evolution had solved the lignin challenge. This arms race, plants inventing lignin to grow tall and resist decay, and decomposers slowly evolving to dismantle it, rewrote Earth's atmosphere. It was a shift just as important as the Great Oxidation Event billions of years earlier, only in the opposite direction, not creating oxygen abundance but preventing runaway accumulation. That extraordinary oxygen spike of the Carboniferous was a fleeting moment, born of a temporary imbalance, and life itself eventually closed the window. This reveals a deeper truth about our atmosphere. It is not just a physical shell surrounding Earth, but a biological construct sculpted by the metabolism of countless living things over eons. The very air we inhale is, in a profound sense, a product of life. Yet the Carboniferous was only one chapter in a much longer saga of oxygen's rise and fall. To understand the whole story, we need to step back and look at oxygen's journey across Earth's history, a tale of upheaval, balance, and the emergence of complexity. For the first 2 billion years of Earth's existence, oxygen was virtually absent, less than a 10,000th of 1% of the atmosphere. Early microbes thrived without it, relying instead on other chemicals for energy. The skies were thick with nitrogen, carbon dioxide, and methane, more akin to modern Mars or Venus than to today's Earth. Then, about 2.4 billion years ago, something revolutionary occurred. Tiny organisms, cyanobacteria, mastered photosynthesis. They learned to harness sunlight to split water, drawing energy while releasing oxygen as a byproduct. To them, it was merely a clever metabolic pathway, but to the planet, it was At first, oxygen reacted with dissolved iron in the oceans, forming the vast rusty banded iron deposits that miners still quarry today. But over time, these sinks became saturated, and free oxygen began filling the sky. This shift, known as the Great Oxidation Event, was Earth's first atmospheric revolution. Oxygen climbed from near zero to perhaps 1 to 2% of the air, triggering the planet's first mass extinction. For anaerobic organisms, oxygen was toxic, wiping out huge swaths of life or forcing them into oxygen-free refuges. For the next 1.5 billion years, oxygen levels hovered at modest but fluctuating levels, perhaps between. Then around 800 million years ago, another pulse of oxygen surged, the Neoproterozoic oxygenation event, likely pushing concentrations up to 15%. This may have set the stage for the first truly complex animal. Between 550 and 400 million years ago, oxygen continued to climb, eventually reaching near modern levels as land plants took hold and spread. The Carboniferous, as we've seen, brought the most dramatic oxygen spike of all, soaring to 30. Since that time, oxygen has swung up and down but has never again hit such extremes. During the Permian and Triassic, it fell to around 15. Over the past 60 million years, levels have gradually slid downward to today's steady 20. What's striking is how closely oxygen's story mirrors the story of complex life. Each oxygen surge coincides with evolutionary leaps, the Great Oxidation Event paving the way for eukaryotic cells, the Neoproterozoic increase opening the door to the Cambrian explosion, the Carboniferous peak supporting giant land animals. Oxygen has not merely been a background condition, it has been a driver of evolutionary possibility. High oxygen allows faster metabolisms, which in turn fuel bigger bodies, more active lifestyles, and more complex behavior. Today's 21% oxygen represents a long-term balance between production, mainly photosynthesis, and consumption, respiration, decomposition, and chemical weathering. It is just right, high enough for us and other complex life to thrive, but not so high that the planet would burn constantly, as it nearly did during the Carboniferous. Human industry has added a new wrinkle. Burning fossil fuels is causing oxygen to decline ever so slightly, about 0.01% per year. This change is too small to affect our breathing, but it marks another chapter in the endless feedback dance between life and the air it creates. The history of oxygen is a reminder that Earth is not fixed. Its atmosphere has been repeatedly reshaped by life, often in ways unanticipated by the organisms themselves. The air we live in today is the product of billions of years of microbial labor, chemical cycles, and evolutionary innovations, a truly living atmosphere. And when we circle back to the Carboniferous, we see just how strange that imbalance was. Giant insects weren't freak accidents of evolution. They were the inevitable outcome of a one-time atmospheric experiment, when oxygen temporarily soared higher than ever again. Experiments have confirmed the connection. In 2010, researchers at Arizona State raised fruit flies under different oxygen levels for many generations. The outcome was striking. Flies in oxygen-rich conditions grew larger, while those in low oxygen shrunk. Similar studies with dragonflies revealed that when raised in atmospheres mimicking Carboniferous oxygen at 35%, they developed larger wings relative to their bodies, reaching sizes far beyond today's norm. The genetic blueprint for gigantism is still present in modern insects. It's just suppressed by the limitations of our current atmosphere. But oxygen concentration wasn't the only factor. The Carboniferous atmosphere was likely denser overall, perhaps 20 to 25% thicker than today's air, due to its unique mix of gases. For flying insects, denser air meant easier lift and more efficient flight. Meganeura, with its vast wingspan, wasn't just surviving, it was soaring with less effort than it ever could today. Even amphibian-like tetrapods transitioning to land benefited, as the denser oxygen-rich air made breathing easier through their rudimentary lungs. Yet this same oxygen bounty made Carboniferous Earth more flammable than any forest today. At 35% oxygen, even damp vegetation could catch fire. Ancient wildfires, evidenced by widespread charcoal deposits, likely swept through forests with terrifying regularity. Ironically, these fires may have capped oxygen levels, preventing them from rising higher. The more oxygen, the more fires. The more fires, the less plant matter available for burial and oxygen release. A natural feedback loop that stabilized the system. The ripple effects touched everything. Plants grew faster and taller, with lycopsids like Lepidodendron racing to full maturity in just 10-15 years, a blink compared to centuries required for modern giants like redwoods. The oxygen boost supercharged photosynthesis, creating levels of biomass productivity unimaginable today. Yet without strong decomposers, these plants didn't evolve the same chemical defenses against fungi and herbivores, leaving them vulnerable and driving evolutionary arms races in the insects that fed on them. Plant reproduction was also shaped by the atmosphere. Spore-bearing plants thrived in the damp Carboniferous swamps, but as conditions dried, seed plants, able to reproduce without standing water, gained an edge. This shift would eventually dominate global ecosystems. For amphibians, high oxygen allowed impressive growth, with some species reaching lengths of 15 feet, but they remained tethered to water for reproduction, their eggs needing moisture to survive. As habitats dried, this became a critical weakness, paving the way for one of evolution's most revolutionary innovations, the amniotic egg. Around 20 million years ago, the first reptiles appeared, carrying with them this breakthrough. Their eggs, with protective shells and internal membranes, kept embryos safe and moist on land. Combined with scaly skin that conserved water, Reptiles gained a powerful advantage in the drier late Carboniferous and early Permian landscape. As oxygen levels continued to decline, the world tilted in favor of reptiles and away from giant arthropods. With better lungs and circulatory systems, reptiles thrived where others faltered. The transition marked the end of the era of giant insects and the beginning of reptilian dominance, a lineage that would eventually give rise to dinosaurs, pterosaurs, birds, mammals, and ultimately us. In a sense, we owe our very existence to falling oxygen. The Carboniferous oxygen spike was more than a curiosity. It was a pivotal turning point, shaping evolutionary pathways for hundreds of millions of years. Its legacy lives on not just in fossils, but in the coal seams we still exploit today. Those dense black layers are the compressed remains of those ancient forests, storing away the carbon that once fueled Earth's great oxygen high. When we burn that coal, we reverse the process, releasing ancient carbon while ever so slightly reducing oxygen. At about 0.001% loss per year, it won't suffocate us, but it is a reminder that our actions feed back into the same cycle that life has been modulating for eons. Climate change is the more immediate threat, but oxygen decline links us directly to the same planetary story. Ultimately, the saga of oxygen shows that Earth is not a static backdrop for life, but an active partner. Change the organisms, and you change the air. This insight is why astronomers hunting exoplanets see atmospheric oxygen as such a powerful biosignature. Free oxygen is too reactive to persist unless life keeps replenishing it. Detecting it elsewhere would suggest alien microbes reshaping their own skies as cyanobacteria once reshaped ours. The search for oxygen on distant worlds is fueled by what we've learned here on the only world where life has transformed an entire atmosphere. And just as importantly, it reminds us that Earth's own atmosphere is a living system, balanced delicately by the push and pull of biology and geology. Understanding how oxygen availability shapes life gives us a window into our own biology. Humans, like every other mammal, are completely dependent on oxygen. Our fast metabolisms and our energy-hungry brains demand a constant, efficient supply of this gas. That is why our species developed such advanced systems for breathing and circulation, lungs filled with millions of tiny alveoli that maximize gas exchange, and blood rich with hemoglobin that can transport oxygen to every cell. These traits are the evolutionary legacy of life forged in an oxygen-rich atmosphere. Insects, by contrast, rely on a passive tracheal system where oxygen diffuses through tubes directly into tissues. Vertebrates took a different path, evolving active breathing and pumping mechanisms. This shift meant that as animals grew larger, their oxygen supply could scale up with them, allowing high-energy lifestyles even during times when atmospheric oxygen fluctuated. Our dependence runs so deep that even small shifts in oxygen availability affect us profoundly. Travel to high altitudes where oxygen pressure is lower, and the consequences are immediate. Breathlessness, fatigue, dizziness, or in severe cases, altitude sickness. Spend long enough in such environments, and the body adapts, increasing red blood cell production to capture the limited oxygen. This response illustrates how tightly human physiology is tuned to oxygen. On the opposite side, we have situations where oxygen is provided in excess. Hyperbaric chambers, which expose patients to high oxygen pressures, are used to treat conditions such as decompression sickness, carbon monoxide poisoning, or certain infections. The surplus oxygen dissolves directly into blood plasma, bypassing hemoglobin and delivering fuel directly to tissue. But too much oxygen is dangerous. Prolonged exposure can lead to hyperoxia, damaging lung tissue, the nervous system, and other organs. Life evolved within a narrow comfort zone, and like the Goldilocks story, oxygen levels must be just right, not too little, not too. Our current biology reflects Earth's present-day equilibrium of roughly 21% oxygen at sea level. Step outside that range, and trouble begins. If we were transported back to the Carboniferous, when oxygen reached 35%, the results would be disorienting. Our nervous systems would falter, our coordination would collapse, and seizures could follow. We are not built for such oxygen-saturated air. Hundreds of millions of years separate us from those conditions. On the other hand, if oxygen dropped to 15%, as it did during the Permian, we would feel as though we were permanently at high altitude, gasping for breath with every step. Our bodies are locked to the atmosphere we evolved in, not the atmospheres of the distant past. This leads naturally to questions about our future in space. As humanity plans to settle or explore other planets, we will face atmospheres that are nothing like Earth's. Mars, for example, has an atmosphere less than 1% the density of ours, with only trace oxygen. Any colony there would require sealed, engineered environments with Earth-like air. Some visionaries even propose terraforming Mars, altering its climate and air to mimic Earth. But such a task would demand not only raising temperature and pressure, it would also require carefully crafting the right oxygen balance for human survival. We are products of Earth's chemistry, shaped by its specific atmospheric recipe. The story of the Carboniferous reminds us that when atmospheres shift, life must adapt or die out. The end of that period saw oxygen fall, triggering extinctions but also forcing innovation. Some creatures vanished, while others evolved to match the new rule. Insects, once capable of gigantic forms, responded by shrinking and refining their breathing systems. Over time, they diversified spectacularly, spreading into nearly every niche on Earth. Today, insects are smaller than their giant ancestors, but they are far more successful, dominating terrestrial ecosystems with millions of species. Adaptability, not size, secured their survival. This resilience is a hallmark of life. When conditions change, new winners emerge. The close of the Carboniferous oxygen surge did not mark the end of life. It merely shifted the balance of which organisms thrived. For us, living through another period of rapid environmental change, the lesson is sobering and hopeful at once. The warning is that altering atmospheric chemistry drives biological change, often with unpredictable consequences. The reassurance is that life as a whole has survived upheavals far greater than those we are currently creating. Unlike ancient species, however, humans wield tools and technology. We can construct artificial habitats, engineer new medical or biological solutions, and even dream of shaping entire planets. Yet despite this ingenuity, we remain bound to Earth's cycles, the oxygen cycle among them. The balance between oxygen generation and consumption underpins all life, and our existence depends on its stability. The Carboniferous oxygen spike was a quirk of biology, driven by plants producing oxygen faster than decomposers could recycle carbon. Its eventual collapse came with the rise of fungi and microbes that evolved the ability to digest lignin, closing the imbalance. That balance between production and consumption continues today. It is not fixed, but dynamic, maintained by the combined metabolism of Earth's biosphere. The giants of the Carboniferous, the dragonflies with wings stretching over 2 feet, the millipede-like Arthroplura, stretching 8 feet long, the scorpions the size of cats, were the products of this fleeting imbalance. Once fungi restored equilibrium, the atmospheric window shut forever. Still, the consequences of that hyperoxic world echo into the present. The vast coal seams powering modern civilization are the compressed remains of those lush forests. The evolutionary pressures of fluctuating oxygen levels spurred breakthroughs like the amniotic egg and the dominance of reptiles. Today, new methods let us peer deeper into that ancient world. Amber, fossilized tree resin, sometimes traps air bubbles from millions of years ago. By analyzing them with cutting-edge mass spectrometry, scientists can directly measure ancient gas mixtures. Research on Cretaceous amber confirms that oxygen levels were elevated then, though not as extreme as the Carboniferous, strengthening confidence in these techniques. Plant fossils add another line of evidence. The density of stomata, tiny pores for gas exchange on leaves, tracks ancient CO2 levels. Fewer pores mean abundant CO2, more pores mean scarcity. By counting stomata in fossil leaves, scientists estimate past carbon dioxide, which helps refine oxygen reconstructions. Even the anatomy of ancient insects is being revisited. Using CT scanning and synchrotron imaging, researchers visualize the tracheal systems of both living and fossil insects, revealing that even ancient giants could adjust the diameter of their airways to meet oxygen demands during flight. Though limited by passive diffusion, they were not as rigid as once assumed. Computer models now simulate insect respiration under different oxygen levels, demonstrating that today's atmosphere sets strict limits on insect size. But under 35% oxygen, the upper threshold expands dramatically, aligning perfectly with fossil evidence. These investigations are not merely about the past. They also inform our search for life elsewhere. Mars, once wetter and thicker aired, might have hosted life shaped by very different atmospheric constraints. Other worlds with oxygen-rich or oxygen-poor environments could evolve creatures with respiratory systems unlike anything on Earth. By studying Earth's history, we refine the signs we should look for in exoplanet atmospheres as potential biosignature. Meanwhile, the Carboniferous warns us about our own future. While we won't see another oxygen peak, human activity is rapidly altering atmospheric chemistry in another way. Carbon dioxide. Since pre-industrial times, levels have soared from about 280 ppm to over 420 ppm in just 2 centuries. An eye blink in geological terms. Just as falling oxygen once reshaped life, rising CO2 will remake ecosystems. Some organisms will adapt and flourish, others will collapse. The pattern is certain, even if the details remain unpredictable. Seen through the lens of Earth's past, today's climate crisis takes on a broader context. Life has always endured atmospheric upheaval, but individual species and ecosystems often vanish in the process. In the Carboniferous, excess oxygen made Earth a world of fire, where even damp forests could ignite. Our world may become one of heat, where greenhouse gases trap energy with devastating consequences. Different forces but the same lesson. Atmosphere and life are inseparable. What makes the Carboniferous story so compelling is its illustration of Earth as a single integrated system. Atmosphere, oceans, rocks and life are in constant conversation, each shaping the others. Plants created the oxygen surge, fungi ended it, and animals evolved in response. This feedback loop is what makes Earth a living planet rather than a lifeless rock. Modern Earth system science continues to emphasize these connections. To understand climate, biodiversity, or air chemistry, we must consider the whole. The descendants of Carboniferous giants still fly and crawl today. Modern dragonflies, though smaller, retain the same body plan, compound eyes and hunting skill of their enormous ancestors. Millipedes and scorpions carry the legacy of creatures that once dwarfed them, scaled down to fit today's atmosphere. These links remind us that we are not cut off from that ancient world. It lives on in DNA, in the coal that powers cities and in the oxygen we breathe. Ongoing research continues to reveal how oxygen shaped not only anatomy but also behavior. Elevated oxygen may have fueled the evolution of complex flight maneuvers in insects, providing extra energy for neural and muscular control. As oxygen declined, animals had to invent new strategies, adapting their activity patterns and energy use to survive leaner time. These shifts likely influenced the course of reptile and mammal evolution, including the development of efficient lungs that later supported dinosaurs, birds, and ultimately humans. All of this reinforces that the Carboniferous oxygen peak was not a strange anomaly. It was part of a much longer atmospheric saga that still unfolds. Today's balance of 21% oxygen, 78% nitrogen, and trace gases reflects only the current state of a constantly shifting equilibrium. With human activity now injecting massive amounts of greenhouse gases, we are altering this balance in ways unprecedented in speed, if not in scale. Just as fungi closed the Carboniferous oxygen window, our actions are reshaping Earth's chemistry again. Whether life thrives, stumbles or transforms under this new atmosphere depends on how both biology and humanity respond. In the end, the story of the Carboniferous reminds us that atmosphere is not just air. It is a living, evolving system, inseparably tied to the fate of life itself. The lesson of the Carboniferous isn't that changes in the atmosphere are inherently destructive. In fact, Earth's air has never remained fixed. It has always shifted and evolved. The real danger lies in the pace of change. When it happens slowly, over millions of years as it did during the transition from the Carboniferous into the Permian, life has the chance to adapt. But when the shift comes rapidly, as it is today, species often lack the time to adjust, leading to extinctions and ecosystem upheavals. Yet even within this cautionary tale, there's reason for hope. The Carboniferous reminds us that Earth has built-in feedback loops that prevent permanent extremes. When oxygen soared too high, wildfires became more frequent, keeping levels in check. Later, when fungi capable of breaking down lignin evolved, they restored balance to the carbon cycle. Earth's history is filled with examples of such self-regulating mechanisms. By studying them, we not only understand past changes, but also learn how the planet might respond to the disruptions we are causing now. These lessons are critical not just for climate research, but also for conservation, policy making, and even planning for life beyond Earth. The enormous insects of the Carboniferous were never destined to endure forever. They were a product of their time, perfectly suited to an atmosphere that was briefly saturated with oxygen. When decomposers emerged and restored equilibrium, their oversized bodies could no longer be sustained. But that doesn't make them evolutionary failures. On the contrary, they were superbly adapted to their unique conditions, thriving for tens of millions of years. Their lineages persist to this day, reshaped by evolution to fit new atmospheric realities. This perspective is deeply humbling. In evolution, success is not about permanence, but about flexibility, about taking advantage of the opportunities that exist in the moment. The Carboniferous giants embodied this principle, and their story is a mirror for our own time. As we move deeper into an era of swift environmental upheaval, the pressing question isn't whether Earth will change. It always does. The question is whether we, as a species, will adapt wisely, and whether we will act responsibly as caretakers of the biosphere. The oxygen surge of the Carboniferous was itself created by living organisms. Plants pumped oxygen into the air faster than it was consumed, while the eventual evolution of lignin-degrading fungi closed that atmospheric window by returning carbon to the cycle. Life has always shaped the air, and the air has always reshaped life in turn. Today, humanity has assumed this role on an unprecedented scale. For the first time, one species has the power to alter atmospheric chemistry globally, deliberately or otherwise. That power carries a weighty responsibility. The choices we make now will ripple across evolutionary paths for countless species, including our own. The legacy of the Carboniferous is all around us. It lingers in the coal seams that power our modern civilization, in the buzzing insects that continue to flourish, and in the oxygen-rich air we inhale every second. That ancient world of towering insects and fire-prone forests has vanished, but its imprint endures in stone, in fossils, in the genetic blueprints of living organisms, and in the very balance of gases that sustains life today. The Carboniferous wasn't simply a curious side story in natural history. It was a time when the very air remade the possibilities of life. Creatures that seem fantastical to us now were once the ordinary inhabitants of Earth, and perhaps that is the most profound lesson of all. Our world, as familiar as it feels, is just one version among many that Earth has worn across its deep history. The planet has reinvented itself countless times, and it will continue to do so. The Carboniferous, with its oxygen-rich skies and impossible-seeming giants, was one extraordinary chapter, a reminder that Earth has been and will be many worlds. Our moment is simply the latest page in that ever unfolding story.